Hello everyone and welcome to this presentation. First of all, let me thank you all for your interest in this work. We are a multidisciplinary group of researchers from the fields of telecommunication and electronics, computer science and sports science from the universities of Granada and Jaén. As you can see on the screen, our work is titled Muscular Patterns Classification in Cross-Country Skiing using inertial sensors and machine learning. Alright, let's get started. As we are all aware, nowadays the inclusion of sensors for sport monitoring can provide information regarding the technique, not only for the improvement of performance and the tracking of the training, but also to prevent injuries due to poor muscular movements. In this context, the use of inertial measurement units, or IMUs, integrated into the skis provides 3-axis acceleration and 3-axis gyro parameters which, in principle, are slightly different depending on the used skiing technique. In this work, we have studied skiing techniques involving a very different muscular work. In short, symmetrical skiing involves a double pulling impulse, being the work of the core and arms much higher than in the case of asymmetrical skiing. So, taking this idea as our starting point, in this work we propose a tool for cross-country skiing technique classification. The main idea is to determine the used technique from the data provided by the IMUs, considering several factors that could affect the patterns during the exercise, as for instance race duration or asymmetry on the leg's strength, among others. For this purpose, a Python script has been developed to process, select, and extract the data sent by the IMUs and synchronize it with the videos, providing different sets for different cross-country skiing techniques. After that, a classification model receives as input the 3-axis information from the accelerometer and the gyroscope to determine the used technique, based on the fact that leg's strength is different for each technique. Now let's see some more details about how we have done this. So, our methodology. First thing to know is that we have placed 3 IMUs to monitor the skiing practice. One in the right ski, another in the left ski, and the third one in the subject's waist using a tight spot belt. The training of a 44-year-old semi-professional male subject has been monitored and analyzed in the indoor ski track located in Xanadu, Madrid. In total, 3 scenes have been monitored with 3 downhill-uphill exercises each one, recording the information with the 3 IMUs. In this slide, you can see the block diagram of the developed Python algorithm. Basically, it processes, selects, and extracts the data sent by the IMUs and synchronizes it with the videos, rotating the video when necessary and cutting the parts of interest out of it to provide different sets for the different cross-country skiing techniques. After processing with Python, in this slide we can observe the schema that summarizes all the components of the classification model. The data processing of the collected gyro and accelerometer data from the IMU, the segmentation and aggregation of this inertial information, and the characteristics of the deep learning model. But let me explain this process in more detail and step by step. Firstly, the gyro and accelerometer data from the IMU, in terms of acceleration values in x, y, and z axes, and the rotation angles yaw, pitch, and roll, is collected with their corresponding timestamp. Then, all these data are segmented, aligned, and aggregated every 100 milliseconds by averaging for each sensor. Subsequently, a 20-point sequence corresponding to a 5-second window of data is constructed. The deep learning model has 2 components. The first one is a 3-layer convolutional neural network, or CNN, that collects the spatial info. The second component is defined by two long short-term memory, LSTM, which are a type of artificial neural networks that extract the temporal sequence by detecting key patterns of change. Finally, a multilayer perceptron layer classifies the spatiotemporal patterns into three classes: left, right, and waist. Now, let's observe in a more visual way an example of how the IMU data changes during the sport practice. Here we can see a comparison of the right and left ski movements during asymmetrical skiing technique. In the upper part, we show the left ski data and below the right ski. In this case, the muscle of the left leg is the one applying more strength during the exercise, which is translated into more pronounced variations in the acceleration data as compared to the right one, and also noticeable changes in the rotation angles, yaw, pitch, and roll. For instance, the roll angle in the right foot is virtually constant as compared to the variation observed in the left foot, the one whose muscle is mostly applying the whole strength. Finally, in this slide we can observe the results obtained for the collected data after applying the classification algorithm. From 743 entries, 696 were correctly labeled by the model, which translates into a 94% correctness rate. Only 47 were incorrectly predicted, coinciding that the real level was there and they were labeled as 1-1, as shown in this confusion matrix. The rest of the metrics calculated from this matrix are shown in the table. The results are encouraging, as accuracy is only most affected for the level 1-1, where accuracy is 84%. Here we have a quick recap of the main points of this work. We have included IMUs in the skis and the waist to obtain the 3-axis acceleration and gyro parameters during the practice of cross-country skiing, which are slightly different depending on the particular technique. A Python script has been developed to process, select, and extract the data sent by the IMUs and synchronize it with the videos. Also, a classification model based on neural networks has been implemented to process the 3-axis information from the IMUs in the skis. Using this development, a 44-year-old semi-professional male subject has been monitored during symmetrical and asymmetrical skiing techniques. The obtained results show a correctness rate of 94%, which is very promising and encouraging in classifying cross-country techniques. Currently, more data is being collected to further train the model and, hopefully, further improve accuracy and create a powerful platform for skiing monitoring and technique classification and prediction. And that brings me to the end of my presentation. We would like to thank the Consejo Superior de Deportes for their support through the projects Sensor for Sport Monitoring and Sensor Sport Lab, and the redes de investigación en ciencias del deporte of the years 2021 and 2022, respectively, partly funded by European Regional Development Funds. Thank you very much for your attention.